Welcome to MedMad Sparrow, where we make medical concepts easy to understand.
All right, let's jump right in. Today, we are exploring one of the most incredible frontiers in all of medicine, the mission to use stem cells to mend a broken heart. And yes, I mean that literally.
First, you really have to understand just how big this problem is. Cardiovascular disease isn't just one of the leading causes of death. It's the leading cause. It's responsible for this staggering number, 32%. That's nearly a third of all deaths around the world. It's a massive global crisis.
So, what's the core issue here? Well, unlike your skin that can heal with a new layer or a bone that mends itself, when your heart muscle gets damaged, it doesn't grow back. Nope. Instead, the body does a kind of patch job, forming scar tissue. And that patch is stiff, it's inflexible, it can't pump blood, and that leads to progressive heart failure. And that, right there, brings us to the central, tantalizing question that's been driving decades of research. What if we could go beyond just treating the symptoms and actually rebuild the damaged heart muscle from the ground up?
So first up, we're going to dig into the heart's fundamental healing problem. You see, its natural repair kit is kind of flawed. It patches the damage, sure, but it doesn't truly fix it. And that's exactly why we need a better way. And that better way, that might just be the stem cell. The best way to think about it is as the body's ultimate master key, a single cell that holds the potential to become any other type of cell. It completely changes how we can even think about repair.
So, what exactly is a stem cell? Well, it's defined by two incredible superpowers. First, it can create perfect copies of itself over and over again. That's called self-renewal. And second, it can transform or differentiate into all sorts of specialized cells, like a nerve cell, a skin cell, or, and this is the key for us, a beating heart cell.
Now, not all stem cells are created equal. We've got to talk about the two big powerhouses. On one side, you have embryonic stem cells, or ESCs. They have unbelievable potential, but they come with really significant ethical debates. And on the other side, you've got induced pluripotent stem cells, or iPSCs. And this was a game-changing discovery where scientists figured out how to take, say, an adult skin cell and literally rewind its biological clock, turning it back into a powerful stem cell, all without ever needing an embryo.
But the story doesn't stop there. We've also got another class of players. Let's call them the paramedics. These are mesenchymal stem cells, or MSCs. They're adult stem cells, and they act like on-site medics, coordinating the whole repair process. But what's maybe even more exciting are exosomes. These are the tiny first aid kits that the MSCs release, little packages filled with healing instructions. And this is a huge deal, because it means you might get the healing benefits without ever transplanting a single cell.
And this leads us to a major plot twist in this whole scientific story. See, the original idea of how these cells actually fix the heart, well, it wasn't quite right. The real way they work is actually so much more elegant and way more interesting.
Okay, so the first theory was simple. It was called engraftment. Scientists basically thought of it like fixing a car. You inject stem cells into the damaged heart, and those cells would turn into new heart muscle, just like swapping out a broken part for a new one. Simple, right?
Well, there was a big problem. When researchers actually looked to see what was happening inside the heart, they found that very, very few of the transplanted cells were actually surviving. They just weren't sticking around for the long haul. The new parts weren't staying on the job.
So, if the cells weren't becoming new muscle, what on earth were they doing? This is where the whole paradigm shifted to something called paracrine signaling. Instead of being the replacement parts themselves, the stem cells act more like a foreman on a construction site. They don't lay the bricks, they shout instructions, and release these powerful molecules that direct the existing heart tissue on how to repair itself.
So, what kind of instructions is this repair crew shouting? Well, their signals do a whole bunch of crucial things. They encourage new blood vessels to grow, they protect the existing heart cells from dying off, they calm down dangerous inflammation, they limit the amount of scarring, and they even wake up the heart's own dormant repair systems. They're not rebuilding the house, they're teaching the house how to fix itself.
Okay, so with all of this amazing science, where are we right now? Let's take a hard look at the gap between the incredible promise we see in the lab and the day-to-day reality in the clinic.
And let me be clear, the promise is very, very real. This isn't just theory anymore. This quote right here is from a major, late-stage clinical trial, and it showed that giving patients MSCs after a heart attack led to much better outcomes. We're talking less heart failure and fewer people having to go back to the hospital. That is tangible proof that these therapies can work in actual people. But, and this is a really big but, the reality is that we're not there yet. We still have some major hurdles to clear. We've got to figure out how to keep more of those transplanted cells alive. There are safety concerns like a potential tumor risk with the most powerful cells, or the chance that immature cells could mess with the heart's electrical rhythm. And of course, these therapies are incredibly expensive right now, and the ethical debates are still ongoing.
So, how do we get over these hurdles? How do we close that gap? Well, that brings us to our final section. A look at the next frontier of amazing technologies, all designed to build a better heart.
And I gotta tell you, the solutions researchers are working on sound like they're straight out of science fiction. We're gonna take a quick look at 3 of the most exciting: 3D bioprinting, gene editing, and these cell-free therapies. First up, 3D bioprinting. And yeah, it is exactly as cool as it sounds. Scientists are using these highly specialized printers loaded with a bioink made from a patient's own cells to print, layer by layer, a living, functioning patch of heart tissue. Then, that custom patch can be surgically placed right onto the damaged area for a perfect, personalized repair. Next up, gene editing. With revolutionary tools like CRISPR, scientists are now figuring out how to edit the DNA of stem cells to make them basically invisible to a patient's immune system. Now, just think about what that means. It could lead to off-the-shelf universal donor cells that are ready to go for anyone, making the therapy cheaper, faster, and without the risk of rejection.
And finally, this brings us full circle back to those little first aid kits, cell-free therapies. The big idea here is, why go through the risk and expense of transplanting a whole cell when all you really need are the healing messages it sends out? So this approach focuses on just isolating those exosomes and using them as the treatment. You could get all the benefits of that Paracrine effect without the risks of transplanting whole living cells.
So when you put all of this together, stem cells, bioprinting, gene editing, cell-free therapies, it leaves us with this final, massive, and incredibly hopeful question. Are we on the verge of a fundamental shift? A move away from just managing heart disease to actually truly curing it? The science seems to be suggesting that we may be closer than ever before.